Why do photonic qubits have high error rates? Imagine trying to catch a tiny, fast-moving ball in a dark room. That's similar to what happens when working with particles of light called photons in quantum computers. Photonic qubits, which use these particles to hold quantum information, face many challenges that cause errors. These errors happen more often than in other types of qubits, and understanding why is key to making better quantum machines. One big reason is photon loss. Photons are delicate and can easily disappear from the system. This loss happens when a photon is absorbed or scattered by the environment or the optical components. Since the qubit state depends on whether the photon is there or not, losing a photon messes up the information. Even though we can detect when a photon is lost, it still disrupts the calculation and needs correction. Another problem is phase flip errors. These errors change the phase, or the timing, of the photon's wave without changing its presence. This can happen due to tiny fluctuations in the environment, like temperature changes or vibrations. These phase errors are sneaky because they don't always show up immediately, but they can cause mistakes in the results. In photonic systems, a common way to encode qubits is called dual-rail encoding. Here, a photon is shared between two paths or modes. If one path loses the photon, the system can detect that something is wrong. But this method doesn't fix phase flip errors, which can silently degrade the quantum state. Correcting these errors requires complex error correction codes that spread the information across many physical qubits. Besides photon loss and phase errors, environmental factors like vibrations, temperature shifts, and imperfections in optical devices can cause decoherence. This makes the photons less reliable and reduces the fidelity or accuracy of the quantum state. Generating, manipulating, and detecting single photons with high precision is also a tough task. It requires very sophisticated equipment, which can be expensive and sensitive to disturbances. From the architecture side, these high error rates limit how large and complex a photonic quantum computer can be today. Researchers are working on better photon sources, more efficient detectors, and advanced error correction methods. These improvements aim to bring error rates down to levels where the quantum computer can run reliably for longer periods. In summary, the high error rates in photonic qubits mainly come from photons being lost, phase flip errors sneaking in, and technical challenges in controlling and detecting photons. Overcoming these issues is a big focus in quantum research, as it will help us build more powerful, reliable quantum computers in the future.